So we discussed how to determine the standard cell potential or E naught, right, of any voltaic cell. And so what we want to do now is connect that to the concept of the Gibbs free energy, the standard Gibbs free energy or delta G naught that we had discussed previously. If you recall, what delta G is the maximum amount of work that could be done for a spontaneous process. So we can relate that to the concept of the E cell as follows. So E itself, of course, is just the energy, right? It has a unit of joules per coulomb, which is the number of charge of the electrons that are flowing. And so we can write E as just the amount of work that's done. Now, because work is coming out of these voltaic cells, right? Because we're spontaneously producing voltage, producing energy, we can put a negative here because, again, energy is coming out of the voltaic cell. And so it's the negative of the energy, or we can call this maximum amount of work. That's what the energy is being used to do some work, divided by the coulomb or the number of charge that is produced by that voltaic cell. In that case, we just give it the symbol Q. If we arrange that equation, we get that maximum work is just equal to negative Q times the E cell. Okay, now this E could be the E at non-standard or E at standard. We'll discuss those two separately later on, but right now we're just focusing on the general. Now, the charge here coulombs, but of course, when we do calculations in chemistry, we typically express that as number of moles. So the charge is most of the time converted to the number of moles of the charge. And so to do that, we would express it as number of moles of electrons times a constant we call Faraday's constant times the cell potential. So F here is a value that's equal to 96,485 coulomb per mole of electrons. So it's sort of like an Avogadro's number for electron in this case. We're just saying that there's a certain number of charge per mole of electron. All right, of course, now we want to relate this to delta G. We know that delta G is the same as maximum work, so all we need is replace that maximum work with the delta G symbol, and we get an equation now that relates cell potential with delta G. So this is an important equation that you can use to interconvert between those two quantities, which is the energy that you get out of that electrochemical cells and the voltage. So remember, we've been talking about voltage, but now we are actually able to quantify that in terms of energy. So if I have a 12 volt, battery, for example, that is using a certain type of redox pair, if I know how many electrons that particular redox pair is generating, I can calculate the actual energy I get out of that battery. Okay, so under standard condition, we would put the degree symbol on both of these quantities, the delta G and the cell voltage. So we get delta G standard equals to the negative of N being the number of moles of electron, F is Faraday's constant, and E naught is the standard cell potential. Now, of course, recall that delta G standard is equal to negative RT ln K. We had relate that to the equilibrium constant before. So now we can take that equation, negative RT ln K, let it equal to negative NF E naught, and come up with this equation here, which is showing you the relationship between the standard cell potential and the equilibrium constant. So now this is another way for you to be able to use all those equilibrium constants you learn in general chemistry 2 and connect that to a voltage. This is also a method that people often use to help determine equilibrium constant. You can set up a redox reaction and then using the voltage from equilibrium constant. So when we used to do this without a calculator, this equation is often simplified by assuming that the temperature is done at 298 Kelvin and plugging in the value of the gas constant, which is 8.314, and then plug in Faraday's constant, which is 96,485, you can rewrite that equation to look like this. Okay, so E naught equals to 0.0592 volt over N here being the number of moles of the electron, and then you change the natural log to log. So all that just goes into this number right here, results in that number, 0.0592. So if you put in all the numbers for RT, Faraday's constant, and changing the base of the log from natural log to log base 10, you get 0.0592 divided by N log K. So a lot of times people like to memorize this equation instead of the top one because you don't have to remember as many numbers. In that case, you just remember the 0.0592 and then you have the number of electrons at the bottom and then the equilibrium constant. All right, let's take a look at how we can use this, apply to a situation in electrochemical cells and relating that to both the equilibrium constant and delta G. So here it says that silver occurs in trace amount, right, in some lead and we can use lead to actually displace silver in a single displacement reaction. And this is what the reaction looks like. So the question is, what's the delta G naught and the K for this reaction where you have that single displacement of silver ion to make it into silver metal. So in order for us to do this, we're going to use the two equations that we just learned, which is the E naught connection to delta G naught. And then from there, we can either use the E naught equation with K, or we can just take the delta G naught that we get and convert it to K. Okay, so but either way, what we need to do first is calculate the standard cell potential, or E naught. And of course, in order to do that, I'm going to two reactions, my reduction and my oxidation reaction, and I'm going to need the reduction potential values that I can get from my reference table. So I looked it up already in this case, and given the way the reaction is written, you can see that the lead is oxidized, silver reduced. These are just the standard reduction potential for both of them. So for the reduction of lead, it's going to be negative 0.125. Of course, that's going to be flipped now since the lead actually undergoes oxidation. And then this is the reduction potential for silver. Let me show you the work on the right side here. So this is the actual reaction. Now I flipped it, so that's the positive 0.125 is the actual oxidation potential for lead oxidation. And then at the bottom one, you see the one for the silver reduction is still 0.8. When I add the two reactions together, I get this as my standard cell voltage. Now remember that if I want to balance this equation, which I should because I want to make sure that I get the overall equation correctly at the bottom, what I need to do is multiply this by 2 to get 2 electrons, right? This top one right here is just the same equation. I don't need to change it. And so if I add all that, I get the bottom equation right. Okay, but remember that when you multiply the equation, you don't multiply the E cell. Keep the E cell the same. Okay. However, very important that the equation is multiplied because we want to equalize the number of electrons. So two electrons are produced, 2 electrons are going to be accepted, and those number of electrons is the one that goes here, and that number is 2. So you don't put 4 there. Sometimes people get confused and say, okay, if I give away 2 and I take 2, then that's 4. That's not really true. Remember that one side gives away, the other one takes it. So it's the same 2 electron that's being passed around. So the number of moles of electron is 2. The equation itself has a negative in front of it, right? Delta G standard is negative NF E standard. So negative 2 times Faraday's constant, which is 96,485, times the actual voltage, 0.925 volt, that being joules per coulomb. So if you work out the units here, coulombs cancel, so in the end you just get joules. And the answer is negative. It's a negative number, negative 1.78 times 10 to the 5th joules, which I just converted to kilojoules, so it's negative 178 kilojoules. If you want to calculate the equilibrium constant, which is the second part of the question, you can just use the relationship between equilibrium constant and delta G standard, which is what I did here. Remember that K is equal to E to the power of negative delta G standard over RT. So there's two negatives here, very important. There's the negative of the formula itself, and then the negative here is because our delta G itself is negative. So you end up getting a positive in the power of E there. You get this pretty big number for the K value, which tells you that this reaction is very much product favor, right? That's the interpretation of a large K value. So that's just an example of showing you how to use those two formulas that we just found for delta G standard and for K. Now you can calculate the K using this relationship as well, okay, which is E naught equals to 0.0592 over N log of K. You'll have to rearrange that equation to solve for K, and you'll be able to get the same K value.